It is now, but a moment.
Morning, everyone. Please settle down. We are ready to resume the second half of the morning session. And like everybody else, I'd like to thank the organizers, Daniel, Stefan, Abhiram, and others for putting together this wonderful workshop. It's great to see a lot of friends after 2 years. Our first speaker of this session is Edward Witten from IIS, and he'll be telling us about an algebra of observables for DC space. All yours.
Well, thank you, and thanks to the organizers for inviting us all to Vienna for this conference and also for asking me to speak. So I indeed will be talking about an algebra of observables for an observer in de Sitter space. So another way to say what I'll describe is that I'll give a somewhat abstract answer to the following question. Why is entropy better defined when we include gravity as opposed to the situation in ordinary quantum field theory? So here I'm alluding to the fact that the generalized entropy of Bekenstein, understood as the entropy outside the black hole horizon plus the area over 4G, is better defined than either term on the right-hand side. Both terms on the right-hand side suffer from ultraviolet divergences. The entropy in ordinary field theory is divergent, and Newton's constant G has infinite renormalizations. But as first observed by Susskind and Uglum almost 30 years ago, the divergences cancel in the sum. So entropy turns out to be better defined in gravity than it is without gravity, and we'd like to understand why that's true. In the process, we also will get an answer to the question, in what sense is the generalized entropy actually an entropy? That's a bit of a mystery because the sense in which the area is an entropy is a bit of a mystery. So we'll get at least a partial answer to this question, and it's based on these papers. In ordinary quantum mechanics, when you consider the entanglement between two systems A and B, usually you assume at the beginning that each system has its own Hilbert space, HA or HB. The combined system then has a tensor product Hilbert space, HA tensored HB, and a state psi AB in the combined Hilbert space might be a simple tensor product of state psi A and psi B. That's an unentangled state, and in that state, the A and B subsystems have no entanglement entropy. Or you might have an entangled state, a more general entangled state like this one. In that case, the subsystems A and B are in mixed states, and they have non-zero entropy. The point of what I've said is that in ordinary quantum mechanics, whether or not a state has entanglement and entanglement entropy is a property of the state, not of the system, but of the state. That's not so for entanglement entropy between different regions in quantum field theory. Here's the situation that was first considered by Sorkin almost 40 years ago. We divide space into two regions, A and B, where in the application, B is the region behind the black hole horizon, A is the region outside the horizon. Then you consider the entanglement entropy between quantum fields in region A and those in region B. It turns out that this entropy has an ultraviolet divergence, and the leading divergence does not depend on the state. Every state looks like the vacuum at short distances, so the leading divergence in any state is the same as it is in the vacuum. So this is not a typical situation where entropy depends on the state. It's more inherently a property of the system. Every state has entanglement entropy, and in fact, every state has a divergent entanglement entropy. Now, the root of the difference from ordinary quantum theory is that it's not true in this situation that there are separate Hilbert spaces, HA and HB, for the inside and outside regions. There's only a combined Hilbert space, curly H, for the whole system. What the separate regions have are not Hilbert spaces, HA and HB, but only algebras of observables, curly A and curly B. The algebras of all observables localized in one of the two regions. We can localize an observable in a region, but we can't really localize a quantum state in a region. These algebras act on the Hilbert space of the combined system, so they can be defined by von Neumann algebras, which is just a scary way to refer to an algebra of operators on a Hilbert space. Now, there are three types of von Neumann algebra. A type 1 algebra is the algebra of all operators on a Hilbert space. That's the type of algebra we assume in ordinary quantum mechanics without saying so. And as is familiar, in a type 1 algebra can have pure states, density matrices, and entropies. All the things that are familiar in ordinary quantum mechanics, since a type 1 algebra is always present in ordinary quantum mechanics. It's the algebra of all operators on the Hilbert space of the quantum system. The other types are less familiar. A type 2 algebra does not have pure states, but it can have density matrices and entropies. A type 3 algebra is the worst type. It doesn't have pure states, and it also doesn't have density matrices or entropies. Now, the bad news, first discovered in the 1960s by Araki, is that in quantum field theory, the algebra of observables of a region is always of type 3. So you can think of this as an abstract explanation of the fact that to a region you can never associate it means that to a pure state you can never associate a pure state or a density matrix or entropy, and you can view it as an abstract reason that the entanglement entropy has an ultraviolet divergence that's independent of the state. It's a property of the system rather than the state. However, the experience is that including gravity in a semi-classical way improves the situation, and what I'm telling you today technically is that, at least in the case of the black hole or de Sitter space, including gravity changes the algebra of a region outside the horizon from type 3 to type 2. So when gravity is turned on, even in the semi-classical limit, the region outside the horizon is described by an algebra in which entropy is a meaningful notion, though there is no notion of a quantum mechanical microstate. Technically, we get a type 2-1 algebra for de Sitter space, a type 2 infinity algebra for the black hole. Because of limited time, today I will mainly describe the case of de Sitter space. Well, what is a type 2 algebra? I don't want to assume those are familiar. The most simple way to describe a type 2-1 algebra, which is the simplest type 2 algebra, it's the algebra that acts on an infinite collection of qubits that are in an almost maximally mixed state. So consider a system A of n qubits. We'll take n to infinity, but we can start with finite n. We consider a system A of n qubits maximally entangled with identical second system B, also consisting of n qubits. So here's an example of a maximally mixed state of the combined system. The nth qubit of system A is maximally mixed with the nth, maximally entangled with the nth qubit of system B. So let little a and little a prime be operators that act only on the first k spins or qubits of system A, where k is no bigger than n. And define a function f of a, which is the expectation value of a in the state psi. Well, since I picked a maximally mixed state, the density matrix of system A in this state is a multiple of the identity. In fact, it's 2 to the minus n times the identity. So f of a, which is what was this, it was the expectation value of a in the state psi, but that's the same as the trace of a times the density matrix. So f of a is 2 to the minus n times the trace of a. And therefore, f of a prime equals f of a prime a. They're both equal to this. Another useful fact is that f of 1 is 1, because the state was normalized. And the function f of a has a thermodynamic limit. We can take the limit as n goes to infinity, as long as we consider an operator that only acts on the first k qubits. Adding more qubits that the operator does not act on does not affect its expectation value. So the function f of a has a limit when we take n to infinity, keeping the operator a fixed. And in the limit, it still obeys the same properties I stated, as well as other useful properties that I left out in view of time. Now, because of this property here, f is usually called a trace, and I will write it as one. So formally, we define f of a to be the trace of a, but this trace is not the trace in any Hilbert space representation. That's because we removed an infinite factor of 2 to the n, where n was going to infinity. So this is more like a renormalized trace, but it does have the algebraic property of a trace, namely this. And it has the property that the trace of the identity is 1. So what I've just described, though I left out a few details, is the original Murray-von Neumann algebra of type 2-1, which I'm going to claim is actually isomorphic to the natural algebra of observables in de Sitter space. The other important von Neumann algebras are all constructed similarly. There really are 2 of them, at least for applications I know about. To get a type 3 algebra, which is relevant in ordinary quantum field theory, we start with a state that's fully but not maximally entangled. Fully entangled means that the density matrix on each qubit is invertible. It has no zero eigenvalues, but it's not a multiple of the identity. If you repeat everything I said, but starting with the case that the density matrix is not a multiple of the identity, just assuming it's invertible, everything will be true, including the thermodynamic limit, except the function f of a is no longer a trace. And you get an algebra that has no trace. It has type 3. And that's the algebra in ordinary quantum field theory. The other thing you can do is to repeat the same construction with the maximally entangled qubits, but add infinitely many unentangled qubits. If you do that, you'll get an algebra said to be of type 2 infinity, and I claim that that's the natural algebra of observables outside the horizon of a black hole, although today we will really only talk about de Sitter space. Algebras of type 2 or 3 do not have an irreducible representation in a Hilbert space. Whenever such an algebra acts on a Hilbert space H, it always commutes with another algebra that's also of the same type, type 2 or type 3. For example, we constructed a type 2 algebra, curly A, as the algebra of operators on the A part of a bipartite system AB. So it commuted with an identical algebra, also of type 2, that acts on system B. That was for this particular construction, but the same is true for any construction. Now, as I've already indicated, the difference between a type 2 algebra and a type 3 algebra, or at least the difference that's important for us, is that a type 2 algebra has a trace and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate in the sense that if g of a is any linear function on the algebra, it's the trace of a times a prime for some unique element a prime of the algebra. In particular, if A acts on a Hilbert space H, and psi is a state in H, we can consider the linear function that maps A to its expectation value in the state psi. Well, that's a linear function on the algebra, so, as I just said, it's the trace of A times A prime for some A prime. But in this context, I will refer to A prime as rho, and I'll call rho the density matrix, because the statement, this statement, for this choice of G of A becomes this statement, which is the usual definition of a density matrix in ordinary quantum mechanics. So what I've just told you is that the usual definition of a density matrix makes sense for a type 2 algebra. It has an analog. And therefore, it's natural to call rho a density matrix. So we've learned that a state of a type 2 algebra has a density matrix. Once we have density matrices, we can also define entropies. Entropy is defined, as usual, by the von Neumann formula that S of rho is minus the trace of rho log rho. So a state of a type 2 algebra has an entropy. But in physical terms, the entropy of a state of a type 2 algebra is a sort of renormalized entropy from which an infinite constant has been subtracted. For example, let's go back to the system A of n qubits, maximally entangled with another such system. The A system has entropy n, infinite in the large n limit. Suppose instead we disentangle k of the n qubits, where we keep k fixed as n goes to infinity. Then the entropy is n minus k. Entropy of a type 2 on algebra can be defined by subtracting n before taking the large n limit. So by that definition, the maximally entangled state has maximum entropy, but its entropy is renormalized to be 0. And the state with k qubits disentangled has entropy minus k. More generally, every non-maximally mixed state has negative entropy by this definition. More formally, since the trace was defined in terms of the expectation in the maximally mixed state, this tells us that the maximally mixed state has the density matrix 1, because the trace of A times rho, it will be the trace of A precisely if rho is 1. And notice that 1 is a density matrix since its trace is 1. So the von Neumann entropy of the maximally mixed state is minus the trace of 1 log 1, which is 0, since log 1 is 0. And it's not hard to prove that any other density matrix has negative entropy. So when we discuss entropy for a type 2 algebra, it's a renormalized entropy from which a constant independent of the state has been subtracted, and you can think of that constant as the entropy of the maximum entropy state. Now, as I've already explained in ordinary quantum field theory, the algebras of regions are of type 3. But it turns out, at least for the black hole and de Sitter space, that when we include gravity, things are different. Gravitational effects, even for very, very weak coupling, convert the type 3 algebras into type 2 algebras, which, as I've said before, is an abstract explanation of why gravity makes entropy better defined. The details are different in the two cases, and because time is limited, today I will only describe de Sitter space. Here's the setup. What I've drawn is the Penrose diagram of de Sitter space. So the far future is at the top, the far past is at the bottom. The left edge you can think of as, the left edge represents a geodesic in de Sitter space that we will ultimately think of as the world line of an observer. So I've labeled it that way. And the green region, which is called the static patch, is the region causally accessible to the observer. It's bounded by past and future horizons. And what we're going to do is to describe an algebra of observables appropriate for observations in the static patch. There's a killing vector field of time translations that's future-directed time-like in the static patch and past-directed time-like in the complementary patch over here, the region that is space-like separated from the static patch. Now let H be the generator of time translations. In ordinary quantum field theory in de Sitter space, and also in semi-classical gravity, there's a natural de Sitter state, psi ds, which can be obtained by analytic continuation from Euclidean signature. Now, a famous fact that goes back to the early days of black hole thermodynamics is that correlation functions in this state are thermal at the de Sitter temperature, which is 1 over 2 pi times the de Sitter radius. A slightly abstract way to describe this thermal interpretation is to say that what's called the modular Hamiltonian of the state psi ds is a multiple of the time translation generator, where the multiple is precisely beta. Now, in ordinary quantum field theory, to the static patch we'd associate a type 3 algebra of observables. Including weakly coupled gravitational fluctuations does not qualitatively change the picture. But what really does change the picture is that in a closed universe such as de Sitter space, the isometries have to be treated as constraints. In other words, including gravitons as one more quantum field doesn't qualitatively change things. But what does make things different is that these symmetries are constraints, and the important symmetry here is the time translation generator. Because the symmetry is a constraint, we should replace the algebra of observables A0 by its invariant subalgebra A0 super H. But that doesn't work. The invariant subalgebra is trivial. Basically, any operator that commutes with H can be averaged over all the thermal fluctuations and replaced by its thermal average, which is a C number. So only C numbers commute with H among all operators in the static patch. To get a reasonable algebra of observables, we have to include the observer who's making the observations. Of course, in principle, an observer should be described by the theory not injected from outside. What it really means to include an observer is that we consider a code subspace of states in which an observer is present in the static patch. Then we consider operators that can be defined in low-energy effective field theory in this subspace, though they're not well defined on the whole Hilbert space. As a minimal model of the observer, we consider a clock with a Hamiltonian Q. It's physically reasonable to assume the observer's energy is bounded below, for example, by 0, so I will assume Q is non-negative. Thus, the effect of including the observer is to modify the Hilbert space by replacing what it is without the observer by itself tensored with L2 of R+, where L2 of R+ is the space of functions of Q. R+ because Q is non-negative. The algebra is likewise extended from the naive algebra to the naive algebra tensored with all the observer's operators, and I'll assume that the observer can manipulate the clock in any desired fashion. So this last factor is the type 1 algebra of all operators on L2 of R+, generated by Q and its conjugate. Finally, the constraint becomes the total Hamiltonian of the quantum fields plus the observer. So H is replaced by H hat, which is H plus H of the observer. So the correct algebra of observables, after taking account of the presence of the observer and also the constraints, is the following. We replace A0 by A1, which includes the observer, but we impose the constraint H hat. So the H hat invariant part of A1 is the correct algebra of observables, including both the observer and the constraint. Now, once an observer is present, there are a lot of possible observables that satisfy the constraints. We can gravitationally address any operator to the observer's world line, which we do as follows. For any operator A of the naive algebra, this operator, A hat, commutes with the constraint. P is canonically conjugate to Q, and H is the naive constraint generator. One more operator that commutes with the constraint is Q itself. Now, if you look for more operators that commute with the constraint, you'll soon convince yourself there aren't any. In fact, classic results of Kahn and Takasaki that by coincidence go back to the early days of black hole thermodynamics and also the early days of string theory. All those subjects got started at more or less the same time in the early 70s. Tell us two facts. There are no more operators that commute with the constraints, and the algebra generated by the operators I've told you, A hat and Q, is of type 2. In fact, the algebra we get this way is isomorphic to the type 2 algebra I constructed for you before, acting on the infinite system of almost maximally entangled qubits, if and only if we impose the constraint that the observer energy is bounded below. So for de Sitter space, we want that constraint. If we don't impose it, we get an algebra of type 2 infinity, which is the right thing for a black hole, but not for de Sitter space. Once we get a type 2 algebra, there's going to be a state of maximum entropy with density matrix 1. It's not difficult to identify it. It's the de Sitter invariant state of the bulk fields tensored with the thermal state of the observer at the de Sitter temperature. That's the state of the combined system of the quantum fields and the observer that has maximum entropy. We can draw a few easy conclusions. 2 minutes still? I'll finish in 2 minutes. We can draw a few easy conclusions which harmonize with claims made in the past by others. First of all, since the maximum entropy state has density matrix 1, it has a flat entanglement spectrum. All eigenvalues of the density matrix are equal, namely they're 1, and accordingly the Rényi entropies are constant. This shouldn't be a surprise because in ordinary quantum mechanics, the state of maximum entropy has all eigenvalues of the density matrix equal and all Rényi entropy is equal. Since the density matrix is 1, all states are equally likely, and therefore the probability to observe a given fluctuation is the exponential of minus the change in entropy, where, see, if you observe a given outcome, the entropy is reduced from being maximally mixed to being a state where that outcome was observed. And you can show that the probability of an outcome is precisely the exponential of the entropy reduction due to that outcome. You can ask, and this is the last thing I'll explain, how that's compatible with the thermal interpretation, according to which the probability of a fluctuation with energy E is e to the minus beta E. There's something which is actually quite striking. Even though de Sitter space is a maximally mixed state of maximum entropy, correlation functions in this state are thermal at the usual de Sitter temperature. And one can, from the point of view of the type 2 algebra, give a very short proof. If you ignore the constraints, the time dependence of an operator is defined in the usual way by conjugating with the exponential of the Hamiltonian. And then time-dependent correlations have thermal properties that tell us that are related to the fact that the state can be computed by analytic continuation from Euclidean signature. After imposing the constraint, we replace A by A hat, defined this way, and again we define its time dependence. But now, because H annihilates the de Sitter invariant state, we trivially find that the new operators in the maximum entropy state have the same time-dependent correlators the old operators had in the de Sitter state of the quantum fields. So we learn that the correlators are thermal at the de Sitter temperature, even though the state has maximum entropy. Thank you very much.
We have time for one or two quick questions. There's one here.
You said in quantum field theory the algebra is usually of type 3 and in the context of ADS CFT you showed in the presence of black holes that it's improved to type 2 infinity, but if we consider the boundary theory, which is just a quantum field theory, how do we, is there a nice way to see how this improvement goes about?
Well, first, your question reminds me that I should have mentioned the work of Leutheiser and Liu on precisely the situation you're asking about. That was that motivated my work in the fall. So for any given n, the algebra of all operators on the boundary will actually be of type 1, because you're looking at the whole boundary. However, for any given n, the notion of a black hole is not sharp, because you don't have a precise causal structure in the book. Liu and Leutheiser took the large n limit and observed that for large n, there is an emergent algebra that's actually of type 3-1. There isn't quite time to explain that. But above the Hawking-Page transition, they showed that the natural boundary algebra of simple operators in the field of a black hole is actually of type 3. And what I actually showed in one of the two papers that I cited at the beginning is that 1 over n corrections convert that to an algebra of type 2 infinity. So it's a simple story, but I chose today to explain the de Sitter space rather than the black hole. Time didn't really allow both. I actually think what one learns in the de Sitter space is more interesting, because although I rushed through it at the end, I think it's extremely interesting and challenging conceptually that the entropy is maximal as if the temperature is infinite, but nevertheless you see thermal fluctuations at a finite temperature. But a quick answer to you, though, is to look at the paper from December.
Okay, thank you.
Another question here.
So a de Sitter horizon is observer dependent, unlike
Yes.
the black hole. Although it didn't sound it in the talk, do you think there is any connection between that observation and the difference between the type 2-1 and type 2 infinity?
I think the difference has more to do with the fact that usually we consider a black hole in an open universe. You see, for type 2 infinity, there's no upper bound on the entropy. And it's obvious for the black hole in an asymptotically flat space-time or an anti-de Sitter space that there's no upper bound on the entropy, because both the black hole itself can be arbitrarily big, and also there can be an arbitrary amount of entropy outside. So you couldn't possibly get a type 2-1 algebra there.
Just to follow up, the Schwarzschild de Sitter would then also be type 2-1?
I expect so, but technically I don't understand it. Technically it's different. There's both a cosmological horizon and a black hole horizon. They're at different temperatures. And one needs to modify the analysis to cope with that fact. I think it would be very interesting to do that. But I do expect that... sorry. I'm worried I'm forgetting something, but... yeah, okay. I'm slightly worried about the right answer to that question. I want to say that that's a good problem to analyze.
On that note, let's thank Edward again for a great talk.